So, so this is Dr. Aull, and she has a PhD in bioinformatics.
Hi, everybody. It's a small group, so please feel free to interrupt me. Otherwise, I guess I get to blabber about myself for a while and answer some questions about my career path. Go ahead.
All right. So how did you become interested in computer science?
So I have to go into like my education here too, because I didn't start out in computer science. My first love was biology, and so I was the nerdy little kid who was fascinated by plants and bugs and everything else. And so when I was 7 years old, I read this article, and it was about this research group that was trying to make GMO bananas that would be a polio vaccine. So you'd make bits of polio in this banana, and you could grow it in areas where there wasn't a cold chain. It's hard to keep vaccines refrigerated, and you sell them at the local markets. And by the year 2000, which was science fiction at that point, most of y'all weren't born, that's okay. Science fiction, year 2000, we're going to have these polio bananas in markets all over the tropics where they can't keep vaccines. Did my PhD in immunology. There are a lot of things wrong with that, but I was 7. I didn't know better. So I was like, this is what I want to do. This is my life. So by the time I got to high school, I knew about as much biology as any teenager in the world. So I went to the International Biology Olympiad, won some medals there, won Science Bowl 3 times, and I was ready to go. Let's make some bananas. But 2000 came and went, and we were still real bad at making GMOs. So why are we bad at making GMOs? We know how to make things. We have engineering disciplines for other sorts of stuff. But it became clear that every GMO was its own craft project. And so even if I had a polio banana, it would not help me at all to make a malaria vaccine rice or something like that. I'd be starting from scratch because everything in that particular GMO was hand tweaked, hand done. It didn't have any of that interoperability. And so in other engineering disciplines, you have standards, you have modules. You can expect that you can buy parts from any factory around the world and snap them together like Legos, and they will actually work together. And so at that time, back in 2004, the place to go if you wanted to think about standards and modules in biology, making it into a real engineering discipline, that was MIT. And so that's where I did my undergrad. And I studied with the researchers in the field. I went to work in that for a while. We're still real bad making GMOs. And so what I realized during that period is that we don't have a design vocabulary either. If you're a mechanical engineer, you have these basic simple machines that show up over and over again. Like you've got your inclined plane, you've got your wheel, your axle, and most physical mechanical objects that people make have some of these fundamental parts. And we don't really understand what those parts are for biology. But we have all of these biological systems that work. They do things. They have parts, and we can learn from how those are designed. So the people thinking about that were systems biologists. So I went to grad school in systems biology. And then I had to figure out what I actually wanted to do when I grew up. I knew I didn't want to be a professor, and I didn't really want to go into industry in that area either. We're still really bad at making GMOs, and it makes it hard to get paid because people pay scientists to make things. We're bad at making things. So I looked around, like, well, what do I want to do? And what I realized during this process is that I was drawn to this field because I like to make stuff. And if you put me in a lab, no matter what I'm supposed to be doing, I become the person who makes the technical stuff work. And I was doing a lot that was way outside my job description because I could. And modern biology is data intensive, it's tech intensive, it requires a skill set that a lot of subject matter biologists don't have. And so one way this shows up is data collection. There's a lot of really mindless work that you can do with a robot, you can do it with a few lines of code, you do it with a standard software package. I don't want to do that. My first instinct is to automate all of that because I can. But most biologists don't have that training. They'll just sit there and grind on it, or you'll hit copy and paste a few thousand times. They don't know where to start. And they could, in many cases, get themselves in front of someone who does know, but they'll have to go to the core facility, they have to get permission and the billing codes and get the appointments, and it's just a mess, and they don't think about it. But if I'm sitting there, maybe they'll ask me for a sanity check. Okay, just because Excel can do that doesn't mean it should. Let me show you this other program over here that'll do it in like 4 mouse clicks. So I could be useful. I spent a lot of time doing that when I was supposed to be scrubbing incubators. People got to know if the incubators weren't scrubbed, but just doing such a thing over here. Maybe I should find a job where that's explicitly my job description, to go play with the messy data. And so that's what I do. I play with messy data because biology generates a lot of those. They don't come with instructions. It's just a pile. You have to sit with it for a while. You have to try things. You have to figure out what makes sense. But if you do figure out the right analytical lens to be looking at this, then you can get information that you can't get any other way. You get readouts of really complicated phenotypes, high dimensional data, and you can do things at scale. You can just make millions of measurements. And so that is what I do. And fortunately, I kind of suspected that was where I was going to go. Even though my PhD was systems biology, really, I did it in a bioinformatics department. So that's what it says on my degree. And when I graduated, I became an official bioinformatician. I am all computational. And my job is to help bridge the gap between the biologists, the subject matter experts, and their pile of messy data that they have a hard time working with, to build the tools, build the analysis pipelines to bring them together. And so that's what I do.
What do you value most about computer science, like the skill of knowing coding languages?
Okay, so coding is the art of speaking so that computers can listen. That's all it is, and it is an art form. Like you have to learn it, like you learn a language. Like maybe you've taken your AP US history and you've learned to write the essays in their specific format. Or like, okay, you have your thesis statement and you bring in your evidence like this and you cite it like this. There's a form. Like in English class, you learned, oh, that's a limerick, and so I'd say, oh, that is a piece of code that you're reusing. You need to go store that in a function rather than copying and pasting it everywhere and making a mess. It's the same thing. And so you learn that, you read, you write, you read about writing, you pick up the patterns and you make them part of your practice. And so the reason you would care about this is, at least in the kind of work that I do, is because computers are a force multiplier. So you and I are meat. We're bad at certain classes of things. We're slow, we're tired, we get bored. We're just not good at doing the same thing over and over. We make mistakes. Computers are really good at that, but you have to tell them what to do because they don't know. So having me and a computer opens up an entire world of possibilities that I would not just have available to me if I was sitting in a lab moving clear liquids around. So there are a lot of different ways to use computers. There are people who are basically mathematicians doing the discovery of algorithms, figuring out what the method should be. Say, okay, here is a proof of some theorem in topology. Hi, Kitty. And what that means is that you can do this particular data processing step in this particular efficient way, and it's proven to be correct. And that's great. I'll do that. But there are people who do that. And then there's also another big division is software architects. So that's what my husband does. He works on the main product at Oracle, which is it's one of the biggest database platforms. And somebody's got to like actually write the code that makes that database happen. So he does that. And a lot of the fundamental design choices were made in like the 80s. It's been touched by thousands of people, and now it's got to do new things. Like, okay, let's parallelize this and put it in the cloud without breaking things and without letting our customers break things. Okay, can do that, right? And you know that the code that you're writing to do this is probably still going to be there in like the 2080s. And so if you don't want those engineers to be cursing your name when they have to make it do something that hasn't been invented yet, you've got to design it in some sort of logical, modular, reorganizable way. And that is a specific discipline. That's great. I don't do that either, but a lot of people do. Especially, I work with a team of software engineers. My group does the prototyping, and so take the big messy pile of input, I figure out what to do with it. Like what makes sense. I play with it. I write some research grade code, and then I have some output. Say, okay, this is the input, this is the output. So software team, go. I've usually written it in Python or something that's suited for that kind of rapid prototyping. And the software team will take it, they'll digest it, they'll try to refactor it to make it faster. They'll rewrite it in, I think it's C#. They have their enterprise grade software ecosystem that's been customer proofed, and it's as fast as possible, and it's intended for production. And they're the ones who make that happen. They put my thing into their software as a feature update. And so those are the classes of skills, or some of the main taxonomy of classes of skills that are available in computer science. Okay, go ahead.
So if you could go back in time and give your high school self advice, what would you tell them?
Okay, so I have some meta advice for this. So people give you advice. People love to talk about themselves, but they'll give you advice that works for them. And I'm a turbo nerd. I've known all along that I want to solve hard problems for a living. And so my advice works for me. And if you want to be like a tech CEO, or you want to make simple websites from a tropical beach somewhere, go talk to someone who's done it. The more similar the person who's giving the advice, the better it'll work for you. But okay, that said, if I'm advising myself, I would say go read everything that Cal Newport has ever written. That's Cal as in Calvin and Hobbes, or Cal Berkeley, and Newport's in the beach. But anyway, he wrote Deep Work. He wrote So Good They Can't Ignore You, which is kind of the secret to turbo nerd success. Because if you're really good at something that's rare and valuable, that's currency. You can cash it in to whatever sort of life you want. Say, okay, I want more money. You need me. I'm gonna take whoever pays me the most, or I'm going to take the most awesome problems because that's what I value. Or I only want to work 3 days a week, and I'm going to spend the rest of my time fishing. And you're going to deal with that because you need me. You can cash in that currency for whatever you value. And you can say that the flip side of that is if you get a job that that a 7-year-old would think is awesome, those jobs are kind of invariably not awesome because everybody wants them. Say, okay, I'm going to be a ballerina, or I'm going to be a dolphin trainer. But the reality is, how many SeaWorlds are out there? How many dolphin trainers do they need? And how many people grew up dreaming of training the dolphins? And so what you get is you have people lining up to pay for internships, scrubbing dolphin poo out of the aquarium. Yeah, if you're there for a few years, maybe they'll upgrade you to the chum buckets. They don't have to treat you well. There's a line of people out the door who want your job. So that is turbo nerd currency. Be good at something that is valuable, and you can trade that in for whatever form of awesome suits you. And for college age people specifically, he's got this concept that he calls the failed simulation effect. Like, how do you impress people? How do you make them think that you're awesome? What you want them to think is, wow, how did they do that? I can't imagine how that is possible. And there are a lot of things that are hard that don't pass that test. Like, okay, you are all-state violin. How did you do that? You sat in your room and you practiced your violin and you practiced it some more. It might have been a lot of work, but people understand how you get there. What you want is the things like, oh, you gave a talk to the UN? How does a 17-year-old do that? And the way that you get to those sorts of things is you pick a thing and you start doing it. And as you start doing it, that you'll start to see opportunities that you wouldn't have known about just from your position as an outsider. Maybe you got started volunteering with this organization, and then they had this spot where you gave a talk over here, and then that led to something else, and that led to giving you a talk at the UN. You couldn't have just made that happen, and so that's why. Yeah. Wow. But each of the steps followed logically one onto the other. And so that is, if you have aspirations of getting into a top-ranked college, if you want to go for competitive internships, what you'll find is that these sorts of successes snowball on one another. One success leads to another, and you're not actually working that much harder. You're just concentrating your efforts, and then you're going for things that are not necessarily obvious from the outside. And so that's it. Cal Newport, I would go back in time with a copy of everything that he's ever written, and oh yeah, you're celiac. That would be my 30-second message to my 17-year-old self.
So what challenges did you encounter in your educational path, if any?
So there was a self-inflicted stupid. I tested out of math. And so I had the opportunity to take some advanced math courses as dual enrollment in high school. And so I decided I was just going to take the exam and not have to worry about that. The problem was the courses that I'd taken at my local university were not as hard as the ones at MIT, even though I could pass the test. And so I wandered into my engineering classes. It was expected that I had all of that stuff like entirely 100% down, and I was still a little bit shaky. And it made the engineering courses harder than they needed to be. I should have just, been humble about it, retaken it, because you can never be too good at the basics. You really can't. So that was my own stupid. And there was also, I did struggle with depression while I was in school. I ended up getting help eventually. I did not want to, but I got dragged in, and I talked to the therapist for like 20 minutes and looked at me and said, you have reasonable self-care skills, but you don't apply them when things are going badly at work. Why not? Like, but that's different. If I can't perform at work, then I really am worthless because I don't have anything else. Oh, yeah, that's why I'm depressed, isn't it? And so, yeah, I had to fix that. I'm not good at anything else. I had my entire identity wrapped in being good at school. And then when I wasn't good at school anymore, it did not end very well. And so what I figured out that for my own sanity, I had to have more than one thing going. It's like, you don't want to spread yourself too thin because then you're just not anywhere. But it was important for me to have more than one thing. Say, okay, my experiments are not working, but I just set a personal record in the gym. And so I made a conscious effort get a couple of hobbies that got me out of the house, that got me moving around using my body, and made time for friends. I have met and married my husband, and just had something in my life that was not all science all the time, because science is a harsh mistress. You'll spend most of the time frustrated and just wondering why it doesn't work. And I personally needed something else. And so that was the other lesson that I learned when I was in grad school.
In your opinion, what does it take to be successful in this field?
So I would say you have to like solving puzzles, and not just the fun part of solving puzzles. You have to have a reasonable frustration tolerance. I'm sure you've tried to fix your computer, and why is it doing that? It shouldn't be doing that. And you have to just keep trying things until something shakes loose, something starts making sense. It's not all fun. It can be frustrating. You have to just kind of sit through it, and that makes that moment when you do finally, you finally get the breakthrough, and you see the light coming at the end of the tunnel. It makes it that much more fun. But yeah, it does take kind of a specific sort of patience. So you're like, okay, I am going to wrangle this weird customer data with 4 different forms of apostrophes. And I am going to try to figure out this Heisenberg that only occurs during daylight savings time or whatever. You make it work. It's not for everyone, but if it is for you, then you get to solve puzzles all day, and if it's for you, it is for you, and you'll have a great time. You also have some cats who will assist you in your debugging process, right, Soren? They know I'm a captive audience when I'm in meetings. Go on and get their scritches.
You might have answered this already, I'm not sure, but what did you major in college?
So I was a bioengineering major. I was actually the first person to get that degree, with a little help from a last name that started with A. So the idea was, it was the core courses for the biology major, plus the applications in biology course from all the engineering majors. So there was the MECE course, there was the EE course, there was the fluid mechanics course, the programming course, and so on. And that was exactly what I wanted, honestly, is learn how to be an engineer, and also learn how to apply that to biology. And so that was my undergrad, and my grad school was bioinformatics and systems biology. And I ended up, my specific project was looking at gene expression over time in HIV. And I was doing modeling of that promoter's expression. Very simple little system. It has more complicated behavior than it looks like it should be able to have with the number of components. It was a very small virus. So I did a lot of microscopy, taking pictures of it every 5 minutes to see how bright it was. And also manually clicking on 20,000 cells in order to compare it with my automated image capturing. That goes back to the the sociopathic patients, which you need some of to survive in CS. Get it done. Click, 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 click.
Can you tell us about any other jobs that you've had that have helped you get to where you are today?
Sure. So I graduated from college in 2008, and I took a job at a synthetic biology startup, the place that I'd been working at during college, for summer internships and so on. And I was working in the process department, so I wasn't doing as much programming, but I was doing robots and workflow development, programming the robots, trying to figure out how to make them all work together to produce our product and to do our research. And we're doing some metabolic engineering studies, trying to figure out how to GMO bacteria to make nylon. And so playing with the robots, having them do all that screening. That did not last terribly long because it was 2008 and the economy was on fire. And so they ran out of money. And I found myself with a scientist level title and 22 years old and 7 months of experience. And every job that I was qualified for had herds of 30-something PhDs jumping along. So I like sleeping indoors. And so where I ended up, I took a job at the Harvard dermatology department, and I was a foreskin dissector. And so my job was to go around the maternity wards of Boston and pick up that day's supply of foreskins and bring them back and process those into various samples that would be useful for a dermatology department. I like sleeping indoors, but 3 weeks later, they caught the department sysadmin, among other things, he was running a botnet off of what should have been the department's backup server. And they fired him and he changed the passwords and left. So they realized that they had this nerd from MIT in the back from foreskins. Like, do you know how to do this? Yeah, I do. My parents had run a .com in the spare bedroom back in the 90s, and I would do that kind of stuff because it was better than babysitting. And so I went out to their server farm in the suburbs and I hacked into their server and I got all their data back and I set up their backup server properly. And so I was their sysadmin for a while. And then once I was done, I'd gotten them into a better place. They wanted to set up an automation facility for doing drug screening. And so I'd done a bunch of that too. And so I was doing that and doing various statistics consults on the side, while also, chopping up foreskins more or less half time. And so that gave me exposure to a lot of the human side of things, human biology, because it was in the context of mostly PhDs and DPhDs doing clinically focused biology work on skin cells and skin cancer. And so that was valuable experience to have been mostly focused on lower organisms, bacteria, doing to GMOs over there. It's easier to work with bacteria, and so that was helpful experience for moving into. I did my PhD in human cells, and now I'm working in human genetics. So having had some exposure there is also helpful. It was during that time that I was like, okay, I've moved my interest more towards actually doing doing the data side of things rather than being in the lab, because I figured that was where I wanted to be. I was always trying to weasel out of my lab assistant responsibilities and play with people's messy data sets that they didn't understand, or setting up computational processes for them. I do it, in my spare time, more or less, because I wanted to do it. And okay, that's an actual job that people get paid for, and I want to go do that. But in order to be credible, it is hard to be credible in that field without a PhD. It's a little bit easier on the pure bioinformatics side, because there is less of that tradition in the CS world, in the hard physics sort of world. Biologists and MDs are quite credentialist, and they will take you more seriously if you have a PhD. So I went and got one.
What is your current title or job?
So what is my current job?
Yeah.
Okay, so I work for Thermo Fisher Scientific, which tells you nothing, biotech Borg. The specific piece of the Borg that got assimilated shortly before I joined, Affymetrix, they do microarrays. And so the product that I work on, it's human genetics, focused on screening of people who want to have children. And do you have any heritable diseases that you might want to know about? And so my specific group, we are the algorithms and data analysis group. We work with, as I mentioned, we have a software team. They do the enterprise grade customer facing software. We have an analysis team that handles the routine requests. People who don't have a bioinformatician on staff and they want to have us run their samples and process the data for them, or they want to have some basic arrays designed, things that can be reduced to an SOP, a standard process. We have some people who do that. And my group is the everything else. The stuff where customer requests start to shade into a research project. Can we actually do that? You'll have new features. Can we make this new feature happen? For one example that I worked on is we figured out how to make microarrays do a genetic test for spinal motor atrophy, which is the most common fatal genetic disease of children. And it is it has the cause in about 95% of cases is a specific deletion in the gene SMN1. Problem is you can look at binding intensity for probes that are in that little deletion region. However, there's a second gene, SMN2, and they are almost identical. There's 4 single base changes. And one of those single base changes makes SMN2 like 10% as active. And so because SMN2 is kind of a pseudogene, it's not that important. It varies in the population. So you can have somewhere between 0 and 6 copies in your average 96 well plate full of people. And so you're trying to find people who have 1 copy of SMN1 instead of 2 or 3. If they have 0, they're probably dead. So 1 versus 2, really, on SMN1. In this context where this nearly identical gene is all over the place. And so I worked on doing the data filtering to take the sources of data that were doing more harm than good out, and then taking the more robust signal to noise things and then combining them into an algorithm to try to call, okay, which of these things are SMN1 versus SMN2? Let's identify SMN1 specifically. And so we figured out how to make them do that. Mayo Clinic is actually selling it. So that's out into the world now. And so that's the sort of thing that I do. Worked on tools to help customers curate their data to do that sort of analysis where it's okay, these are things that are probably not good. You don't want to look at those. They're contributing more noise than signal to your sample. Let's filter those out and improve the rest of your results. And do that sort of thing. We do sometimes if the process crashes, we're the ones who have to figure it out. Everything in the manufacturing process, the micro manufacturing process, hideously complicated. Everything is barcoded, everything is tracked. All the machines are producing their logs. And if something goes wrong, then it tends to go to us to drop everything and do the factor analysis and try to figure out what it is. Like we had one process deviation that took months to figure out. It turned out that somebody in Singapore had forgotten to replace the ozone filter in one particular piece of equipment. It had been out for almost a year. And so if it was a bad air quality day in Singapore for the specific couple of minutes where that chip was on this stage of the manufacturing, the more ozone that was in the air in the suburbs of Singapore at that particular moment, the worse the quality of the chips were. It got more and more pronounced as the filter got more and more useless. So yeah, we had to find that. Had to find another process excursion was had a factory in Germany, got a big order for somebody else. And so they cleaned out their warehouse. Normally they would ship us things that were like reagents that were a month or two old. They were shipping us stuff that was fresh off the factory line, and it performed differently. And so we figured that out, and now everything that we buy from them sits in our warehouse for 2 months, just so we can not do that again. So yeah, the manufacturing process improvements. That's your big messy pile of data right there. That's the other thing that we do. Yeah, and sometimes customer complains about this and that, and we try to figure out how to make them happy again. And if we have field support teams, but if the field support team doesn't know the answer, we're kind of the last line of defense. So we are the computer nerds of all trades.
So now we'll go to like participant questions. So if anyone has a question, you can just ask it.
Yeah, I had a question. Did you, like, while you were in school, have any like teachers or specific classes that like really inspired you to kind of want to go into this field?
Yeah, so I had I took some classes with some of the big name synthetic biologists. I definitely wanted to be Drew Wendy when I grew up, and I had I did have some science teachers who were supportive and enthusiastic over the years, but I think I also came in kind of enthusiastically. I think the person who converted me to a systems biologist would be Yuri Aull, who wrote his book about biological modules. I read that and like, okay, yeah, this guy gets it. I want to do that. And I guess I actually learned a good deal from, I was an anthropology minor. And so something that I did not expect to learn from that is some insight into the sociology of the discipline. Like why is it hard to make biology into an engineering discipline? Am I just too stupid to understand? Can I just not get to the level where I can organize biology into neat little boxes and that can interact like Legos? I don't see it. Maybe it's me. And like my anthropology seminar and reading Foucault, of all things, like, no. That's real. Like you can put things into boxes and they'll make some form of sense, but those boxes are not reality. And what's going on underneath is complicated, and it does not want to be put into those boxes. It's like something that people who grew up in the engineering disciplines don't really appreciate is how much power you give up in order to make things able to be modular and composable. It's like you can have, you can take field programmable circuits and evolve them, just have them, toggle the connections randomly and pick the ones that work. And you can evolve them to perform specific logical functions. And you can have these perform better than something that you would design in like your standard circuit diagram. But they only work in the context of that specific chip that they evolved on. Because yeah, you can get away with fewer components, but what's really happening is that you're exploiting the quantum physics because these specific two things happen to be next to each other, and you're refusing to even think about that in order to have your idealized circuit components in your circuit design software. But the trade-off is that your design circuit that ignores all of that will work on any FPGA. It'll work on any system. You don't have to worry about what's next to it or whether there's like a scratch on the circuit board of this particular one. So I did not expect to have that light bulb go on in anthropology seminar, but it did, and it certainly informed the way that I think about how to interact with things that humans did not make. Not entirely sure that answered the question. That was a rant, but that was cat pictures. He's a good boy. He helps me code. Well, sometimes he just gnaws on my ankle. That counts.
All right, so if we don't have any more questions, then we can end the Zoom here.
Okay. Nice to meet you. Good luck.
Thanks. You
Nice
too.
to meet you. Thank you.
Cool. Bye.